Hello, ladies and gentlemen, and welcome back to our third question, and second last question, actually, on the 2009 Galois math contest. So, we have 3 parts to question number 3, because there's quite a big little picture over here on the second page. But there's no preamble to 3, and it looks like it might just be some geometry. I haven't read it, but I think this will probably be a shaded region question, or maybe the A, C, and E are islands or something. I don't quite know. But what have we got here? So A part, find the area of an equilateral triangle with side length 2. So this is sort of some very, very basic, either trigonometry or I think a Pythagorean theorem will help us out, or just, do we remember 30, 60, 90 triangles? It's actually a pretty important formula to know in some cases, the formula for the area of an equilateral triangle, just in terms of its side length. So actually, I'm going to be a little more general. Let S be the side length of an equilateral triangle. Okay, so we'll draw our equilateral triangle. Now, because it's equilateral, it is therefore technically isosceles. Equilateral is a stronger statement, but it is still isosceles in that you have 2 of the sides being the same. Just so happens the third side is also the same. But one of the nice properties of an isosceles triangle is if I drop an altitude, it splits the triangle in half, and more importantly, it splits the base in half. Okay. And what do we need? We need 1/2 base times height for the area. So you could either, so I would probably say something like an altitude, oh, I got an extra D in there that I don't need. Altitude splits the triangle in half. And altitudes, by definition, make a right angle there. So you could either say, well, there's 60 degrees as the interior angle for all the sides of a triangle, just 180 divided by 3. And then you could use some trigonometry to figure out h. Or you could say, well, hey, I've got a right angle here, so I could say that s squared is h squared plus s over 2 squared, and solve for h from there. Or you could you could make the comment that it's a 30, 60, 90 triangle, 30 degrees, 60 degrees, and 90 degrees. And the sides here are always in the ratio of 1 to root 3 to 2. In fact, this would be even more apparent if I wasn't using a general S and I actually used the side length of 2 that they gave me. So either one is a fine approach. I know when the Galois is written, not everyone has taken trigonometry. It's a grade 10 concept. It just depends on whether or not you're sort of taking it as a second semester course or something like that. But whichever way you want, mention 30, 60, 90 triangles. I guarantee the people who are marking know about them. We're going to get that h is root 3 over 2 times s. Okay? And from there, the area is 1/2 base times height. And we get root 3 over 4 s squared. And for our specific question here, for s, not a, for s equal to 2, the area is root 3 over 4, 2 squared, which is 4. So the area here is root 3. Put a little box around it, put a little therefore statement, whatever you want to. And that wraps up question A, or part A. B part. Determine the area of a regular hexagon with side length 2. Now, it's a regular hexagon, and as they have pointed out in their picture, all the side lengths are the same, but it also means all these interior angles are the same. Okay, you can get polygons that have the same side length everywhere, but are not regular in the sense that they all have the same interior angle. That's special. That's something that comes with regularity. For example, with 4 sides, you can get a rhombus. The only one that the equal sides means equal angles is the equilateral triangle, actually. Okay. So what can we do here? Well, if you've ever played around with sort of triangular and hexagonal tiles, you probably know the right approach for this question. We'll draw our hexagon. Well, I'll draw a hexagon. This is not looking like the best hexagon in the world, but that's okay. Doesn't have to be the best hexagon as long as I understand it. What I would do is I would say, well, let's let O be the center. And connect to our corners. Purple, let's say. Okay. So what's going to happen is that all of these happen to be equilateral triangles. What would be the best way to explain it? Well, you could probably say the hexagon is regular, and so its center is actually its circumcenter. That's pretty helpful, and that tells you that all of these are the same side or something like that. Or you could say, well, these lines that connect centers to the corners, you can say they bisect the interior angle of 120 degrees. Okay, so they are each 60 degrees. So we get 60 degrees here, 60 degrees here, 60 degrees here, 60 degrees here, and so on. Other things you could say is, well, bisymmetry. Each angle at O is 60 degrees. In some way, you're going to have to use the fact that it's a regular hexagon. And you say, oh, well, then we've broken it down. We have 6 equilateral triangles of side length 2. Okay, but from A, the area of each of these is root 3, so the area of the hexagon is 6 of these little equilateral triangles, so it's 6 root 3, and there we go. Okay, I would say to get full marks on this, you have to make some justification that it breaks down into 6 equilateral triangles. That's 1, maybe 2 marks, depending on how much of a stickler they're being. You have to call back to part A. We worked this out. It's root 3, and our final answer is 6 root 3. Okay. Alternatively, I mean, I'm not saying this is the only way to do it. You could, just like we did in the last question, where we got sort of a general formula, you could probably, if you wanted to, just derive the formula for the area of a regular hexagon in terms of its side length. That's doable. I think it's a little much to ask on a grade 10 contest, especially because they set you up in part A. There's the equilateral triangles, and just about anyone who's messed around with a regular hexagon before knows that you get equilateral triangles. They're just asking us to make that connection again. Okay. Alright, so 3C. Last one in C part, and this should be interesting, whatever it is. In the diagram, regular hexagon ABCDEF has sides of length 2, again. Using AC and E as centers, portions of circles with radii 1 are drawn outside the hexagon. So, portions outside. Okay. Using B, D, and F as centers, portions of the circle with radius 1 are drawn inside. And they do connect up because we split 2 into 1 and 1. So, okay, that makes sense. So that's, I guess, is what they've got going on. These 6 circular arcs join together, okay, to form a curve. Determine the area of the shaded region enclosed by the curve. Okay. Alright, so it kind of looks like, if we complete these circles, it looks like some circles, but then there's this big area in here, and I'm not entirely convinced I can figure that out. But what could we do? I think they're sort of giving us the hint to talk about inside and outside the hexagon. And I think if we break it down into this area, and this area, which are sectors of the circle of 240 degrees, and then we take the area of the hexagon, which we know from B part, that's why they asked us that in B part, and chop out these white areas here, which are sectors of a circle that have 120 degrees as their sector angle. I think that's doable. Okay, so what might we do? I would start by saying, because if I'm about to use a formula, I should mention what formula I'm going to use. Recall the area, let's say, of a circular. I did need the A there. Of a circular sector of theta degrees is, well, it's the full circle, which is pi r squared, but then we want a fraction of that circle, theta degrees out of 360 degrees. So that's what we need there. Alternatively, you could do this in radians, but why bother? Okay, so just draw a little picture. That's what we're talking about. So they know that I know what I'm talking about. Okay. So the area of the shaded region is 3 sectors. And you might want to duplicate a picture and sort of indicate this. So I'm going to say these 3 sectors here of 240 degrees, and they even tell us the radius is 1, plus the area of the hexagon minus, so this stuff here is the blue, and now minus the green, these sectors here. And I would color code it. I mean, it's nice to have a blue, black, red pen with you for that sort of stuff, or just some pencil crayons. That way you can erase it if you make a mistake. Minus 3 sectors of radius 1 and 120 degrees. Okay, hexagon, subtract those, gives me this black portion, and then I add on the blues. Okay, well this isn't a problem. So it's 3 times 240 degrees out of 360 degrees, pi r squared, plus, and this is where part B comes in, 6 root 3, minus, and then 3 sectors of 120 degrees, pi, again, the radius is 1 squared. Okay, so we'll and I do mention where you got your 6 root 3 from. You mentioned that came from B. That way they just say, oh, they copied their answer from B. Even if you got B wrong, you're fine. So the area we want is 240 out of 360 is 2/3. 1 squared is just 1. And then plus 6 root 3. You know what? We can drop the brackets there. In fact, we can drop the brackets with all of it. 3 times 2/3 pi plus 6 root 3 minus 3, and then 120 out of 360 is 1/3 pi, and then 1 squared is 1. So this is 2 pi plus 6 root 3 minus 1 pi, or pi plus 6 root 3. All right. And, this even makes sense. We do get... So what can we do here? Just to really illustrate this. We're chopping parts out of the hexagon, but if I split my outer sectors, they're accounted for by one of each of these, and then I've got these 3/3 of a circle of radius 1 left over. So sort of these two parts here cancel. And you could probably make an argument based on that. And then, so we still maintain the full hexagon area. And then we're left with 3/3 of a circle. Well, what's the area of that circle? It's just going to be pi 1 squared, or pi. So there we go. And that's it. We finished all 3 parts for C. We've got one more question to go, and that'll be question number 4. We'll take a look at that in the next video. Thank you guys, as always, so much for watching, and I'll see you next time.